Here we have a triangle ABC. We know two sides of this triangle. Side AB is 16, side BC is 10. And the third side we don't know, and that's what we need to find. Another thing we know is that a triangle has two angle bisectors. AE is bisecting angle A. It's split it in two congruent parts. And CE is splitting the angle C into congruent parts. We have 2 points, point D on the side AB, which split that side in two halves, and point F that splits the side BC such that BF is 7, CF is 3. And the line DF, connecting points D and F, goes through point E. So how are we going to do this? Well, first let's do a little bit of looking. And one thing we noticed that E is the point of intersection of two angle bisectors. And we know from geometry that in a triangle, all three angle bisectors intersect at the same point. So which means that BE is going to be an angle bisector as well. The other thing we know about this point E is that is the center of a circle that is inscribed in this triangle ABC. So inscribed circle is a circle that doesn't come out in any part outside of the triangle ABC. And that's the largest circle you can put inside of the triangle ABC. The sides AB, BC, and AC are tangent lines to this circle, which means that there is only one and only one point that this circle shares with line AB. Let's call it H1. There is one point that a circle shares with line BC. Let's call it H2. And the point which the circle shares with line AC, we call it H3. Now, what we're going to do next is we're going to connect those H1, H2, and H3 with the center of a circle E. So all these three segments have the same length, equal to the radius of the circle. There's another property that relates the circle and a tangent line, and that is that the tangent line, like AB, and this radius EH1 are at 90 degrees to each other. In a similar way, EH2 will be at 90 degrees to BC, and EH3 will be at 90 degrees to AC. So let's get rid of the circle, we don't need it anymore. And what we're going to do now is to calculate the area of a big triangle ABC. And we're going to do it by splitting it into three triangles. That blue, orange, and gray. So let's consider triangle AB, the blue triangle. The area of this triangle is the height or altitude. That will be EH1 times the side or length of the side of this triangle AB and divided by 2. Right? For the orange triangle, it's a half EH2 times BC. And for the triangle AEC, it will be half EH1 times AC. The whole big triangle ABC is the sum of those three triangles. Okay? And we're going to get a formula like this. So there are two unknowns in this formula. We don't know R, we don't know the radius of the inscribed circle, and we don't know X. Okay? So let's move on. And the next thing we're going to do, we're going to calculate the area of the small triangle DBF. And we're going to split this triangle into two triangles, blue and orange, and calculate the area of each triangle separately. If you look at the blue triangle, its area of it is half EH1 times dB. and area of the orange triangle is half EH2 times BF. We can find both areas, add them up to get the area of dBF, and get a formula like this. The next thing we're gonna do is we get rid of this R, because we're not really interested in R. Nobody asked us to find it. So to do this, we're gonna just divide the area of one triangle, big triangle ABC, by the area of the smaller triangle dBF. In this case, we're going to have a relationship that has only x in it. So what we're going to do now is we're going to calculate the area of triangle dBF and triangle ABC using the sides AD, BD, BF, and CF. Okay? So first, we're going to draw a line DG that is parallel to line AC. And what we notice that the triangle at the top, DBG, is similar to triangle ABC. And that's because if you look at angle A of the big triangle and angle D of the small triangle, those angles are corresponding angles for parallel lines, and corresponding angles for parallel lines are congruent. And the second thing is, if you look at angle B, that angle, both of these triangles share. Well, in this case, that angle is congruent to itself. So we find that these two triangles are similar by two angles. And in similar triangles, the sides are proportional, which means that the ratio of the respective sides should be the same for all the sides. And that means that DB divided by AB is the same as DG divided by AC, and the same as BG divided by BC. Okay? We know DB over AB, it's half, so we know the ratio of the other sides. The other thing we know about similar triangles is how the areas related to each other. If we know the ratio of the sides of the similar triangles, we know that the ratio of the areas of similar triangles should be the ratio of the sides squared. And in this case, we related the area of the small triangle on the top to the area of the large triangle ABC. We know from this that BG is half of BC, which makes BG 5, and that makes GF 2. Now we'll look at the top two triangles and we'll try to relate them to each other. Now notice the purple and orange triangles have a common vertex, D, and what we're going to do, we're going to draw an altitude, dk, from that vertex. Now notice that altitude is an altitude for both of those triangles. So now if I want to calculate the area of the purple and the orange triangle, I will do it by taking half of dk times the length of the side. So in case of purple triangle, it's going to be BG, and in case of the orange triangle, it's going to be FG. And now what I'm going to do, I'm going to divide the area of the orange triangle by the area of the purple triangle. In this case, we get rid of dk. And we found how the areas of those two triangles are related to each other. And we can use it to calculate the area of a triangle DBF, which is sum of areas of these triangles. And we calculate the area of triangle DBF via the area of triangle DBG. But the next thing is to notice that we know how to relate the area of triangle DBG to the area of a triangle ABC. And this way we relate the area of DBF to the area of the big triangle of ABC. we can rewrite it in a different way, like this. So we found the ratio of the area of the big triangle to the area of the smaller triangle in a different way from the inscribed triangle. So now we have two formulas that's supposed to give us the same result. So from these two formulas, we can find x by equating right-hand sides and solving this linear equation by multiplying both sides by 15 first and subtracting 26, and then simplifying the right-hand side to find the final answer.